Hello, wonderful people. Here we are. It's chapter 7, Momentum. We started the chapter yesterday, and today we are on to section 7.2. So, if you have some momentum, which means you have a mass and you're moving along at a velocity, how do you change that momentum? Well, you can imagine that you have to apply a force, and you have to apply that force for some duration of time. You can't just touch it instantly. And so, what changes momentum? Impulse. And we will discuss what exactly impulse is. Okay, so a little bit of review. Linear momentum, and 99% of the time we just call that momentum, is the product of the mass and velocity of an object. Like velocity, linear momentum is a vector. So that means it has a direction as well as a magnitude. There's the equation, P for momentum equals mass times velocity. And the SI unit is kilogram times meter per second. So what is momentum and what is not momentum? All objects have mass, and anything that has mass has an inertia. But in order for an object to have momentum, it has to be moving. So the amount of momentum is dependent upon two variables: how much matter is moving, the quantity of mass, and how fast it's moving. A bus can have a large momentum, even if it's moving slow, because it has a large mass. And there, do you see the equation underneath the bus? A big mass times a small velocity equals a big momentum. A bullet can also have a large momentum. It may have a small mass, but if you get it moving at a high velocity, and do you see it down there? A small mass times a big velocity equals a big momentum. Now, an object at rest, it has no momentum. It doesn't matter how big it is, it has no momentum. And this is the key difference here. Momentum is not the same as inertia. The elephant that's standing still has inertia. It has some resistance to motion, but it doesn't have momentum. And that's very simple when you just plug it into the equation down underneath the elephant. Momentum equals mass times velocity. If velocity is 0, momentum is 0. So, inertia is another property of mass that resists changes in velocity. Inertia depends only on mass. And since it only depends on mass, there's no vector to it. So inertia is a scalar quantity. Momentum is a property that has velocity in it. And velocity is, of course, a vector. So that means momentum is also a vector. Let's do a couple questions. Determine the momentum of a 60 kilogram halfback moving east at 9 meters per second. 9 meters per second, that's pretty fast. It's just you multiply 9 times 60, break out a calculator. I can do that one in my head. 540 kilograms times meters divided by second going east. B, a 1,000 kilogram car moving north at 20 meters per second. 1,000 times 20 is 20,000. So momentum equals 20,000 kilograms times meters per second due north. C, a 40 kilogram man moving southward at 2 meters per second. 2 times 40 is 80 kilogram times meter per second south. And that's what a bunch of the homework questions from yesterday were, just that kind of straightforward. Force. So force is mass times acceleration, as you see in the top right corner there. Now, the strength of my legs can make me jump up onto a box. It takes me about a second to do that. So I can jump up and land on a box that's 1, maybe 2 feet up off the ground. Using those same legs, I could also run for 10 seconds upstairs and get up 2 flights of stairs. So how long that force is applied matters. I can apply it for just under a second and jump up a couple feet, or I can apply the force for several seconds and go a few flights up. So the important part here is how long the force is applied. Does that make sense? So We keep track of force and time using a new unit. It's called impulse. Impulse is just force multiplied by time. And there's the equation right under it. I for impulse equals force times time. Now remember, force is a vector quantity, so impulse is a vector quantity. Also, like most of the time, half the time, we show t as delta t. So the equation looks like that. I equals F delta T. That is the impulse equation. Are you okay with me so far? So force is the rate of change of momentum. Let's talk about that. So momentum changes. Remember, momentum is mass and velocity. So if I'm moving along with some velocity, that momentum is going to change when you apply a net force because you're going to change the velocity. Now, the inverse of that is also true. So the first sentence is momentum changes when a net force is applied. And then you can also say the inverse. If momentum changes, then a net force was applied. Oh, in that red dot, it says created. So if momentum changes, forces are created. So you need forces to change momentum. So if you see a momentum change, there's a force somewhere. And of course, if momentum changes quickly, large forces are involved. All right, there's a lot of writing here. Don't freak out. We're going to ignore most of it. For those of you that are comfortable with the writing, it'll be up on the screen for a while. But if you're just following my voice, I just want you to read this equation right here with me. And it starts off simple. F equals mass times acceleration. F equals ma. We've been looking at that for a long time now. Now, acceleration is a change in velocity over time. Do you remember that? Acceleration just means that you're changing the velocity of something. Now, we can change the speed, but we can also change the direction. Let's just worry about changing the speed for now. So all I'm saying is I'm taking that A and I'm turning it into that, the definition of acceleration, the change in velocity divided by the time that it takes to change that velocity. If you're okay with this, it's all downhill from here. That was the hard part right there. So now I'm going to take and eliminate the mass times acceleration in the middle. I'm just going to say F equals mass times delta V over T. So now I've got this equation, which is still F equals ma. Now I'm going to do something algebra. I'm going to take this T and I'm going to multiply it over to this side. So if I take that T and I multiply a T over here and a T over there, I get F times T on this side, and the T over T cancels out over here. I just brought the T from the bottom to the top. You know you can do that from algebra, right? And so now I've got this equation. And this is impulse. There it is, force times time. And if you go back a couple slides, oh, that was on the other slide, sorry. Force times time, that is what impulse is. And over here is mass times velocity. Mass times velocity. Is that ringing a bell? Oh, come on, people. Think a little. Mass times velocity. We've been talking about it. Mass times velocity is momentum, right? Are you with me there? So if I just take the F equals ma equation and I just change it just a little bit and I get the T over here, now I have impulse on this side and momentum on this side. I think that's pretty cool. You may not be impressed, but I'm impressed. So I'm giving myself a big pat on the back. And if you're keeping up with this, you deserve one too. So now I've got impulse over here and momentum over here. And this section, 7.2, is about introducing you to impulse, force times time. And so this is the grand conclusion of the day. Impulse, force times time, is what produces a change in momentum. You have to have a force, and it has to be applied to an object for some amount of time. And once you do that, Now you're changing the object's momentum. If that doesn't make sense, then go back and rewatch whatever parts of the video you need to, or maybe, call me crazy, send me an email or post a question or something. But if you get this, then from here on out, it's downhill, okay? There's one more thing. You see this F times time equals mass times the difference in velocity? Well, now instead of just saying the difference in velocity, this part of the equation is momentum. So it's the change in momentum. Are you okay with that? Because that's what this equation is saying. There's the net force times time equals the change in momentum. And we're down here, mass, F equals ma with t's in there. Oh, here it is. Mass times the change in velocity is the change in momentum. So that's what I did from here to here. I did mass times the change in velocity equals the change in momentum. Are you okay with that? That might be a bit of a weird step. Okay, so this is the equation we're going to use and we'll put in our notes. But 90% of the time when we're writing the equation out, we're going to write it using MV because I'm going to give you a bunch of different masses and velocities that you're going to have to solve for. So you are going to have to get used to the idea that P equals MV. Just like F equals MA, P equals MV, and you have to get used to switching between those two because we're always substituting in. And why do we do that? Because it's hard to measure a force, especially out there in the real world. You can stand on a bathroom scale and measure a force, your weight going down in a nice static setting. But when two cars collide, you can't get a bathroom scale out there to see what happened. But what you can do is look at the skid marks or rewind the video, and you can see the changes in velocities. And you can measure masses of cars pretty easy. So when you that's the bread and butter. We measure masses and velocities, and then we calculate the changes in momentums. And you would be surprised how much this comes up even in everyday life, from accident reconstruction towards all kinds of engineering applications, because things move, right? There's a lot of things out there in the real world that are moving around, and if an object is in motion, then it has momentum, and you got to watch out. Sometimes momentum can be dangerous. That bus coming down the street, that momentum will kill you. And there are plenty of other places where momentum kills too. So, yeah, people in the real world deal with this stuff. So let's move on and see if we can do some basic definitions here. So will be in the notes. The product of a force and the time the force acts is called impulse. That's the straight up definition of impulse. Impulse is also a way to measure a change in momentum because it is not always possible to calculate force and time individually since collisions happen so fast. Another way to say it, thank you. Oh, there's the classic example. Right. So anybody, I don't care if you've never even seen a boxing match, you understand the idea that if somebody's going to punch you in the head, you don't throw your face forward into the punch like the guy on the right. You ride the punch. Ask any boxer, that's what you do. You let your head roll back with the punch, and it doesn't hurt as much. So there's the guy on the left riding back with the punch, and the guy in the forward is going flying into the punch, and that hurts more. Why? Here it is. The change in momentum. If you have a long time, if the fist is in contact with the guy's jaw for a long time while he's moving backward, then the time gets bigger, and then the force gets smaller. But if you go flying into the punch, then the time that you're in contact with the glove is small. So a small time makes for a bigger force. In both cases, you're having a change in momentum. But the trick of the matter is, if it occurs over a small time, you have a big force, and big forces hurt. But if you stretch it out over a long time, then you have a small force, and that doesn't hurt as much. Did that make sense? I hope so, because that's the definition of impulse And all the applications that we're going to do from here on out are just basically explaining this idea using different stories and some equations and numbers. So here is our impulse equation again. Force times time equals the change in momentum. And impulse is expressed in kilogram meters per second. Another way to call that is a Newton second. We'll get into that in a couple of slides. Impulse is defined as the product of force acting on an object and the time during which the force acts. Force times time. The symbol for impulse is I, so there we go, I equals Ft. So let's do a quick little example. A 50 Newton force is applied to a 100 kilogram boulder for 3 seconds. What is the impulse of the force? Impulse equals the force, 50 newtons, times the time, 3 seconds, 150 Newton seconds. Please note, we didn't need to know the mass of the object in this example. The mass didn't matter. So here is where we go over the units. So I said Newton second, right? Newton times second. And there's the second, and there's the second. So here I'm going to take 1 Newton, and I'm going to turn Newton into the units. And Newton is force, mass times acceleration. So there's mass and there's acceleration. Kilogram times meter per second squared. Now what happens if you have a second on the top and a second squared on the bottom? They cancel, so 1 second is still left on the bottom. So Newton second equals a kilogram meter per second. I don't know why this mustache is in the middle of this. Okay, so impulse is equal to momentum. Well, different in units. They're saying newtons times second is different than kilogram meter per second. No, it's the same thing. Okay, this isn't my slide, or else I would have changed that. A Newton second is the same as kilogram meter per second. All right, so let's do 2 or 3 problems, and then we'll call it a day. Oh, and once again, there's a mistake on the slide. This should not be a J, it is an I for impulse. If the halfback experienced a force of 800 newtons for 0.9 seconds to the north, determine the impulse. Impulse equals force times time, and that's what we have here. Force times time. So we plug in 800 newtons in 0.9 seconds. I definitely need a calculator for this one. Oh wait, no, I can just move the decimal point over. Well, it's written there, but 720 is correct. 720 Newton seconds. Now you can write it as Newton seconds, or you can say it's 720 kilogram meters per second. I don't care which. You must have the units correct though. There's one, let's do another. A tenth of a kilogram model rocket engine is designed to deliver an impulse of 6 Newton seconds. Anybody ever launch rockets? That's how you buy the motors, the engine. When you go to the store to buy them, they list the impulse as 6, 7, 8 Newton seconds. If the rocket engine burns for 3/4 of a second, what is the average force the engine produces? Stupid J should be an I. Impulse equals force times time. Input. Oh, what are we looking for? The average force. So now they're giving us the impulse, 6.0 Newton seconds. That's on the engine. We know that it burns for 0.75 seconds. So if we divide by 0.75, bring that over, there's the division, and this divided by that, those cancel. So force equals 6 divided by 3 times 4. And if you need a calculator, not a problem. But 6 divided by 3 is 2, 2 times 4 is 8, so I know in my head that that's the correct answer. The force is 8 newtons. 8 newtons doesn't sound like a lot, but when you build those model rockets, that's why we make them very, very light. 8 newtons will shoot that thing up into the sky in a blur. You'd be amazed at how fast they go up. And quite frankly, this is the part where I would normally take you out onto the football field and shoot off some model rockets, because it's showing off this, but mostly just because it's a ton of fun. So I'm sorry we're not doing that. Corona. Okay, last problem. You know what? I'm just going to leave that up on the screen. I think you can walk through that okay. So please go do the homework. If you have any problems, give me a call, a text, an email, whatever. Thank you for your work and good luck, and we'll see you tomorrow. Bye bye.